Hello everyone, I am Dr. Krishna Sarker. Here in this session, I will be going to discuss about transfer function calculation from electrical networks. This is linear control systems problem number 3 or example 3. Lecture series on linear control systems and lecture number 15. So our topics: transfer function calculation from electrical networks, and this is problem number 3. Transfer function calculation and example 3. What is the example 3? Find the transfer function of the given electrical network. This is our given electrical networks: R1 resistance, another resistance R2, and one capacitor C. And this is the source Vi of t, and the connection diagram. This is the connection diagram. And V0t equals to output voltage. V0t equals to output voltage and Vit equals to input voltage. So what is the transfer function? Transfer function means output divided by input, or Laplace transform of output divided by Laplace transform of input, and all initial conditions at zeros is called that transfer function. So Laplace transform of V0t divided by Laplace transform of Vit. This is our main target, or this is our main focus. So Vit equals to input voltage, V0t equals to output voltage. Then procedure for finding the transfer function of the electrical networks. First, solution step number 1. The given electrical networks shown in figure A, and determine the transfer function. This is our figure A. Vi of t input voltage and V0t output voltage, R1t resistance, R2 another resistance, and capacitor C. And this is the current IT. So this is the given transfer function and time domain transfer function. Given electrical network. This is the given electrical network, time domain electrical networks, and this is the frequency domain electrical networks. So first, next point, draw the given network figure B in S domain. With each inductance by SL and each capacitance by 1 by SC. In this case, Vi of t, this is the input voltage, time domain to frequency domain, Vi of S. This is the V0t, frequency domain, V0S, time domain to frequency domain. And I of t, loop current or mesh current, this is equivalent to I of S, and capacitor C equivalent to 1 by SC. So this is the frequency domain circuit. Then next point, use KCL, KVL, mesh analysis, node analysis to write networks equation. So by using KCL, KVL, mesh analysis, node analysis, first write the differential equation actually, then solve the simultaneous equations for the transfer function calculation. So first calculate VIS and next calculate V0S, and then ratio between V0S by VIS. This is our target. This is the transfer function. Then transfer function calculation. Apply KVL in mesh 1 of the given networks. This is the given networks: R1 resistance, R2 resistance, capacitance C, input voltage Vit, and the output voltage V0t. This is the input current, loop current I of t, and this is the mesh 1 and this is the mesh 2. Then what is the input voltage? Vi of t equivalent to drop for R1 into R1 into I of t, and for R2 into I of t, and for capacitance 1 by C into IT dt. This is the equation number 1. In this case, this is the input voltage. This is the input voltage Vit, For R1 resistance, R1 into IT because loop current IT, and for R2 resistance, this is the R2 and the loop current or mesh current, I of t, and this is the capacitance. For capacitance 1 by C into integration IT dt. This is the equation number 1. Then for output voltage V0 or mesh KVL analysis, in mesh 2, V0T equals to output voltage. V0T output voltage equals to, for resistance R2 into IT and plus 1 by C capacitance. For capacitance 1 by C into IT dt. This is equation number 2. So applying KVL in mesh 1 of the given network, this is the VIT, and apply KVL in mesh 2 for output voltage V0T equals to this. Then what is the transfer function? Taking transfer function calculation. Transfer function taking Laplace transform of equation 1 and 2 with assumption that all initial conditions zeros, because this is the transfer function definition. VIT equals to R1 IT plus R2 IT plus 1 by C IT dt. V0T equals to R2 into IT plus 1 by C into IT RT. Then taking Laplace transform from equation 1. For equation 1, what is the Laplace transform? This is the Laplace transform for VI of t equivalent to Laplace transform VI of S. R1 constant, I of t Laplace transform I of S. R2 has to constant resistance, and I of t equivalent to Laplace transform I of S. 1 by C constant again, and I of S equivalent to IS by C. This is the form. Then taking Laplace transform for second equation, V0T equivalent to V0S, and R2 into IT, R2 into IS plus 1 by SC into I of S. So this is the Laplace transform V0S, and this is the constant value IT equivalent to IS, and already discussed 1 by C constant, and IT integration IT dt equals to IS by S. So this is equation number 4. This is the equation number 4. Then what is the transfer function? Definition of transfer function. Transfer function equivalent to Laplace transform of output divided by Laplace transform of input. All initial conditions are zeros. And another form, Laplace transform of output response or effect, Laplace transform of input variable or excitation. This is also called cause. And all the initial conditions are zeros. This is the transfer function definition. Then step number 5, calculation of transfer function. Calculation of transfer function from equation 3 and 4. What is the equation 3? Vi of S equals to R1 IS plus R2 IS plus 1 by SC into IS. V0S output voltage equals to R2 into IS plus 1 by SC into IS. Then therefore equation 4 divided by equation 3, and the transfer function is, this is the transfer function V0S by VIS equivalent to what? V0S by VIS. This is the V0S. So this is the V0S, and input voltage. This is the input voltage, and this is the output. This is equivalent to this, and this is the input form, and this is equivalent to denominator terms. This is equivalent to denominator terms. Then IS common and cancel, and we get V0S by VIS. Output voltage divided by input voltage equivalent to R2 plus 1 by SC, R1 plus R2 plus 1 by SC. Or IS cancel. This is the numerator term, and this is the denominator terms. This is the denominator terms. Then LCM SC, and we get SC R2 plus 1, SC R1 plus SC into R2 plus 1. Therefore, the transfer function of the network is given by V0S by VIS equals to SC into R2 plus 1, R1 plus R2 into whole into SC plus 1. And this is equivalent to 1 plus ST1, 1 plus ST2. That means where T1 equals to what? T1 equals to these terms. So 1 plus ST1 and T2 equals to this term. So 1 plus ST2. The block diagram representation is shown in figure. This is the input voltage VIS and this is the output by input ratio 1 plus S21 by 1 plus ST2. So this is the controlled output. This is the reference input. So V0S by VIS equals to 1 plus S21 by 1 plus ST2. Transfer function of the network is given by V0S by VIS equals to 1 plus S21 by 1 plus ST2, where T1 equals to CR2 and T2 equals to R1 plus R2 whole into C. And strictly proper transfer function. This is the because from the transfer function V0S by VIS equals to here numerator power and denominator power are same because SS power 1 and SS denominator S power equals to 1. So this is a strictly proper transfer function where T1 equals to CR2 and T2 equals to R1 plus R2 whole into C2. That means this is the M equals to N from case number 3. M equals to M equals to 1. Numerator terms M equals to 1. And in this case, S to the power N, that means N equals to 1. That's why this type of transfer function is called strictly proper transfer function. Then V0S by VIS equals to 1 plus S21 by 1 plus S2. Here number of zeros equals to number of poles. The above transfer function having the simple poles are at S is equal to minus 1 by T2. Simple poles. That means this term is equals to 0. 1 plus ST2 equals to 0. That means S is equal to minus 1 by T2. And similarly, numerator terms and the simple zeros are at what is the position of zeros? S is equal to minus 1 by T1. Similarly, 1 plus ST21 equals to 0, then S equals to minus ST1 equals to minus 1, ST1 equals to minus 1, and S is equal to minus 1 by T1. This is the position of zeros. Then what is the pole zero location? This is the real axis. This is the imaginary axis. This is the imaginary axis. And what is the pole position? One pole position at S is equal to minus 1 by T2. So this is the pole position at S is equal to minus 1 by T2. And another pole S is equal to minus 1 by T2. S is equal to minus 1 by T2. Zeros. One not, this is T2, this is equivalent to ultimate T1. S is equal to minus 1 by T1. At S is equal to minus 1 by T1, only 1 0, and S is equal to minus 1 by T2, only 1 poles. So, and all the poles and 0 left hand side of the S plane, that's why system will be stable. This system will be stable. All the poles and zeros left hand side of the S plane. Then pole zeros of a transfer function. The transfer function of a control system is defined as the ratio of the Laplace transform of the output variable, response or effect to the Laplace transform of input variable excitation. This is also called excitation, also called cause, assuming that all the initial conditions to be 0. A 0 is indicated by a small circle 0. The points at which the denominator polynomial P of S equals to 0 are called the poles of the system G of S. A poles are indicated by a small cross. A 0 of the transfer function G of S becomes 0, and at poles it becomes infinity. The denominator polynomial for the transfer function is called the characteristics equations. So thank you.